Hello everyone, today we have OpenQuant question number 17, 100-yard dash. There are 6 runners in the 100-yard dash. How many ways are there for 3 medals to be awarded if ties are possible? The subpart of this question below in parentheses is extremely important to help understand what constitutes a tie and how rankings would be awarded if a tie were in place. It says that the runner or runners who finish with the fastest time receive gold medals. The runner or runners who finish with exactly 1 runner ahead receive silver medals. And the runner or runners who finish with exactly 2 runners ahead receive bronze medals. To help illustrate what this part of the question is saying, if 2 people receive gold because they tie for first place, there will not be a silver place. Instead, the next person who has the next best time would then receive bronze medals. And it's also important to consider that there could be multiple of these bronze winners. There could be 1, there could be 2, all the way up to 4, because there are 6 total participants. Let's now enumerate the different ways the race could end. We could have only gold medals awarded. We could have only gold and silver medals awarded. We could have only gold and bronze medals awarded, and the 4th and final case is having all 3 gold, silver, and bronze medals awarded. And this problem reduces down to counting the number of ways each of these 4 cases could occur, summing them up, and getting the total number of ways that our game could end. Let's start with case number 1. If only gold medals are awarded, there must be at least a 3-way tie for first place. If that last statement didn't make sense to you, I highly urge you to pause the video and rationalize why this statement is true. However, there could be more than a 3-way tie. We could have 4, 5, or 6 people tying for first place. And as a result, the total number of ways that the game could end with only gold medals awarded are 6 choose 3 plus 6 choose 4 plus 6 choose 5 plus 6 choose 6. For the second case, we have only gold and silver medals awarded. In order for any silver medal to be awarded, this means that only 1 person can come in first place. So we have 6 choose 1 ways to select our first place winner. We then, however, multiply this value by all the different number of ways that we could have silver medals awarded. However, there needs to be more than 1 winner in second place. Otherwise, we would have a bronze medal. As a result, the number of ways to get our silver medalists, given that 1 person has received a gold medal, is 5 choose 2 plus 5 choose 3 plus 5 choose 4 plus 5 choose 5. Our third case is when only gold and bronze medals are awarded, and for this to occur, exactly 2 people need to have received the gold medal. If more than 2 people receive it, we have our first case, and if less than 2 people receive it, we have our second case. So we have exactly 2 people of the 6 receiving our gold medal, and then for each of that initial condition, we have to count the number of ways that bronze medals could be awarded. Now we could have 1 person getting third, or 2, 3, or 4. So just like for the second subcase, we'll sum over all possible values for our bronze medalists. And lastly, we have our gold, silver, and bronze case, where one person receives a gold, one person receives a silver, and at least one person receives a bronze medal. By a very similar logic as the first three cases, we have 6 choose 1 ways to select our gold medalists, then 5 choose 1 ways to select our silver medalists, and then for our bronze medalists, we could have either a single person winning it or a 2, 3, or 4-way tie. So this would be 4 choose 1, 4 choose 2, 4 choose 3, plus 4 choose 4. Alright, perfect. Let's now compute this value. I'd like to do so to prove that such a gaudy expression can actually be solved even in a time-constrained setting. Let's now compute the number of ways that case number 1 could occur. This is 6 choose 3 plus 6 choose 4 plus 6 choose 5 plus 6 choose 6. So 6 choose 3 is equal to 6 factorial over 3 factorial over 3 factorial, which is equal to 6 times 5 times 4 over 3 times 2 times 1. So here we have 2, and then we have our 2's cancel out. This is equal to 2, or 20. Then we have 6 choose 4, which is also equal to 6 factorial over 4 factorial times 2 factorial. Again, both of these expressions were derived simply using the definition of the combination function. So this is equal to 6 times 5 over 2 times 1, or 15. 6 choose 5 is equal to simply 6, and 6 choose 6 is equal to 1. So our total value for case number 1 is equal to 20 plus 15 plus 6 plus 1, or 42. And we'll underline it just for clarity. Let's now compute the summation of case number 2. So in this one we have 6 choose 1, which is just 6, times this whole expression right here. And to solve that, I'd like to introduce a combinatorial identity, which is very useful for such problems, and it's that the summation from I equals 0 to n of n choose I is equal to 2 to the n. What exactly does this mean? It simply means that 5 choose 0 plus 5 choose 1 all the way up to 5 choose 5 is equal to 2 to the 5th power. And again, you could replace this 5 with any n and replace that 5 with any n, and the identity would hold true. And we'll actually use this throughout the rest of the problem to help us evaluate expressions quickly. So I'll box it in so that you guys can see it again as we continue moving forward with this problem. Okay, so going back to this expression right there, it's also equal to 2 to the 5th minus 5 choose 0 minus 5 choose 1, simply because those are the two expressions that are omitted from the sum right here. This is also equal to 6 times 32 minus 1 minus 5, or 6 times 26, or 156. Perfect. Now the third subcase is equal to 6 choose 2 times this sum right there. 6 choose 2 is also equal to 6 choose 4, which we calculated right up there. So we know it's equal to 15. 15 times the sum right here that is underlined, which is equal to 2 to the 4th minus 4 choose 0, which is equal to 15 times 16 minus 1, or 15 squared, which is equal to 225. And the fourth and final case is 6 choose 1 times 5 choose 1, which we know is equal to 6 times 5, or just 30, times this sum right here, which happens to be the exact same one we just calculated, and which we know is equal to 16 minus 1, or 15. So 30 times 15 is equal to 450. Is the total number of ways that the game could end with a gold, silver, and bronze medal awarded. Great, so all we have to do now is compute the sum of these four values. So our solution is equal to, let's see, 42 plus 156 plus 225 plus 450. The summation of these two is 198. Summation of these two is 675. Adding these two values together, we get 870. Okay, here's some mental math. 675 plus 200 minus 2, or 875 minus 2, or 873. So that right there is the solution to this problem. Thank you for watching. Thank you for watching. If you enjoyed the video, please like, subscribe, and check out our parent site, OpenQuant.co. Of course, if you have an alternative solution, please comment it below. We'll pin the best one. Thank you.